Hello and welcome to the Unit 8 Section 3 video on graphing and interpreting quadratics. So in the first part of this section, we're going to talk about graphing quadratics in both standard and vertex form. And then in the final part of this section, we're going to talk about interpreting quadratics in real-world situations. So let's start off by graphing in standard form. Here is a look at standard form, y equals ax squared plus bx plus c. Remember, a cannot be 0 because if a is 0, we do not have a quadratic. There's going to be a few different items that we are going to want to know to be able to graph a quadratic. Okay, so let's run through what those are, starting with the direction of the graph. You can find out what the direction of the graph is by looking at your a value. Okay, that is your leading coefficient. If a is positive, the graph is concave up. If a is negative, then the graph is concave down. We can also get the y-intercept fairly easily by looking at our c value. The y-intercept, again, is where the graph crosses the y-axis, and you get that y value of your intercept by just looking at what c is. Okay, so all you have to do is pull c out of that form. Next, we have the maximum and minimum point. Okay, a maximum occurs when the parabola is concave down. A minimum occurs when the parabola is concave up. The axis of symmetry, we're actually going to have a formula for this. It's the vertical line that splits the graph in half. Okay, so it's symmetrical on both sides of that line of symmetry. And we use the formula x equals the opposite of b over 2a. Okay, the opposite being negative in this case. Okay, so negative b over 2a. And then the last piece of information we're going to look at is the vertex. We can get the vertex, which is either the highest or lowest point on the graph, depending on if you have a max or min. We will use the x value from the axis of symmetry, and we'll plug that into the equation to find the y value that goes with it. Okay, and that will give us our x and y for our vertex. So let's run through a couple of examples of how this is going to look. So we're going to identify each key feature in standard form. So with A, the direction of the opening is going to be concave up because that leading coefficient is 2 and it's positive. So since it's positive, it's concave up. The axis of symmetry, we're going to use our formula, x equals the opposite of b over 2a. So b is 6. A is 2, so you're going to plug those two numbers in for B and A respectively. And then from here, you're just going to solve. Negative 6 over 4, which reduces to negative 3 over 2. Then to find the vertex, we need to find the y that goes with this x. So we have the x value of our vertex. We need to plug this into our equation to get our y. So we do that by plugging in negative 3 halves everywhere there is an x. And then we evaluate this. So negative 3 halves squared, 3 squared is 9, 2 squared is 4. Okay, so you just square the top, square the bottom. When you square the negative goes away. And then I'm going to go ahead and multiply 6 times negative 3 halves, so that's 6 times 3, which gives us 18 halves. And then 2 times 9 fourths gives us 18 fourths. I'm going to go ahead and get a common denominator. 18 halves becomes 36 fourths. Multiply the top and the bottom by 2. And then 1 is, of course, 4 over 4. And then you just subtract your numerators, and you get negative 22 over 4, which reduces to negative 11 over 2. So our vertex is at negative 3 halves and negative 11 over 2. Our y-intercept, you're just going to pick off the c value. So don't forget the negative in front of it, so our y-intercept is 0, negative 1. And finally, our max/min value, you need to tell what we have. So since we're concave up, we're going to have a minimum, and it's going to be at y equals negative 11 halves. So it's the y value of your vertex. All right, in example B here, our direction of the opening, since we have a negative out in front, we're going to be concave down. Our axis of symmetry, again, we're going to use x equals negative b over 2a. And we plug in our b, which is negative 1. our a, which is negative 1/2, and that's going to give us negative 1 over 1, which is just negative 1. Plug negative 1 into your equation. Everywhere there's an x, we put negative 1, and then we evaluate it and solve, and get 11/2 as our y value for our vertex. So our vertex is at negative 1, 11/2. The y-intercept, we just pick off our c, which is 5, so 0, 5. And then we have, since we're concave down, we are going to have a max, and that's going to be at 11/2. Y equals 11/2. So to graph in standard form, you're going to find and graph the axis of symmetry, determine and plot the vertex, choose 2 points on one side of the axis of symmetry and plot them, and then reflect those points across the axis of symmetry, and then connect with a smooth curve. So let's go through this process of actually graphing, now that we know how to find some of the key features. So let's start with A here. Our axis of symmetry is going to be negative b over 2a. We plug in our b, which is negative 4, our a, which is 1, and evaluate and get that our axis of symmetry is at 2. Then we're going to find our vertex. We've got the x, we need to find the y by plugging the 2 back in. So everywhere there's an x, we put a 2. 2 squared is 4. 4 times 2 is 8. And then when we put together all those terms, we get negative 2. So our vertex is at 2, negative 2. Now we're going to put in a value for point 1. So since our axis of symmetry is at 2, we can either choose to use 1 and 0, or we can use 3 and 4 as our points. I'm going to opt to use 1 and 0 because those are easier numbers to work with. So I'm going to plug in 1 everywhere for my x and see what y goes with it. And I get that y is negative 1 when I do the math. Now for point 2, I'm going to plug in 0. Or actually, we don't even have to plug in 0, because if we plug in 0, we're just going to get our y-intercept, which is 2. Okay, so let's plug in negative 1 and see what we get. We will end up getting 7 as our y. So negative 1, 7 is our next point. So then from here, we take this information and we just go ahead and graph it. So our axis of symmetry we found was 2, so we graphed that here. Our vertex was 2, negative 2, so we graphed that down here on the axis of symmetry. And then we did our points. So we had 1, negative 1, so that went here. We had negative 1, 7, which went here. We had our y-intercept, which went here. And then after you plotted all 3 of these points, you reflect them across the axis of symmetry. And then you connect it with the smooth curve. So this is what your final product should look like. Let's take a look at example B. The axis of symmetry, negative b over 2a. B is 2, a is negative 1/2. And so we find that our x is 2. We plug our 2 back into our equation to get the y that goes with it. So our vertex is at 2, negative 4. Just like the previous problem, I'm going to opt to go with 1 and negative 1 as my points. Or we could even go with 0 and 1 as our points. So here's just a showing of why C is our y-intercept. Because if I plug in 0 here and 0 here, these two terms are going to go away, which just leaves the negative 6. So that is why the y-intercept is our C term. Okay, so we have 0, negative 6 as one of our points. If we plug in negative 2 for another point, that's going to give us negative 12 for our y. So we get negative 2, negative 12. And then we can go in and graph it. Okay, so you probably see here on the graph, again, first, you're going to plot your axis of symmetry, plot your vertex. Then here's our 2 points, 0, negative 6, and 2, negative 12. And then you reflect those across the axis of symmetry and connect your curve. You can probably see why we didn't use 1 or -1 as points is because they don't fall cleanly on the grid. So that's why we opted for 0 and -2. You'll want to use even numbers because notice we have a 1/2 out in front. And that 1/2, you want to work with even numbers to get the fraction to go away. So that's why we used even numbers here. All right, let's talk about graphing in vertex form now. The vertex form of a quadratic is given here. Y equals a times x minus h quantity squared plus k. Graphing in vertex form is actually a little bit easier because it's a little bit easier to get the information that you need off of it. So let's take a look at some of that information. So the direction of the graph, just like in standard form. If a is positive, the graph is concave up. If a is negative, the graph is concave down. So you're going to be looking for what your leading sign is. What sign do you have at the front of your equation? For the y-intercept, you are going to have to do a little bit more work for this. Again, where the graph crosses the y-axis, you're going to have to substitute 0 in for the x value and then simplify. Okay, for the maximum and minimum point, again, you have a max when the parabola is concave down and a min when the parabola is concave up. So that's the same as what we've already dealt with. For the axis of symmetry, you are going to, again, find the vertical line that splits the graph in half. And this one's easy because you don't even have to use an equation for it. It's just going to be the x value of the vertex, which is h. Okay, so whatever your value for h is, that is your axis of symmetry. Speaking of the vertex, your vertex is going to be located at the highest or lowest point of the graph, just like before. But this time, you don't have to really do much work for it. It is just simply the ordered pair HK. So you just read your H, you read what your K is, that's your ordered pair, that is your vertex. So let's take a look at an example and find some of these key features. So for A, we have the direction of opening. Since we have a negative out in front, we're concave down. The axis of symmetry, our h value is 2, so x equals 2. For our vertex, our hk is 2, 3, so it's just 2, 3. For the y-intercept, this is the one you have to do a little work for. So we're going to substitute 0 in for x, and then we're going to solve it and get -1 for our y, so our y-intercept's at 0, -1. And then our max or min value, just like before, since we're concave down, we have a max, and we're going to pick off our y value from our vertex, which is 3. For B, our direction of the opening, since we're positive out in front, is concave up. The axis of symmetry, we have a 1 here, but it's a positive 1, which means we have a -1 following the minus sign, because in the form, if we go back up to the form, the h follows a minus sign. So what we really have here is x minus -1 to make it positive. So our axis of symmetry is going to be at -1. Vertex, -1, -6. Read our h and our k. For the y-intercept, you plug in 0 for x, and then you solve. So we get -2 as our y-intercept. And then our max or min, we're going to have a min since we are concave up, and the y value from our vertex, which is -6. So to graph in vertex form, it's going to be very similar to what you did in standard form. You're going to find and graph the axis of symmetry, determine and plot the vertex, choose 2 points on one side of the axis of symmetry and plot them, reflect the points, and then connect with a smooth curve. So essentially exactly what we did for standard form. It's just a little bit different how we get the information. So let's start with this first example. For this first example, for the axis of symmetry, we read our h value, so that's x equals 2. For our vertex, we read our h and our k, so that's 2 and 1. Our first point, we are going to pull for our first point to something that's on the left of 2. So let's start with 1. So we're going to plug in 1 for ax, and then we're going to solve and find that our y value that goes with x is 3. And so our point is at 1, 3. Now let's do 0. And essentially what we're finding here is our y-intercept. And our second point is at 0, 9. Okay, I'm kind of rolling through this math because you just follow the order of operations. Do parentheses, exponents, multiplication, and then add. So, just like before, you're going to graph. You're going to start with your axis of symmetry, plot your vertex, plot the 2 points on one side, reflect them onto the other, and then draw your curve. For example B, our axis of symmetry is going to be at -1. Our vertex is going to be at -1, -3. That's our HK. So since we're on -1, let's go to 0 first for our first point. So x equals 0. We're going to follow our order of operations and get the y that goes with it. So 0, -6, that's our y-intercept. Then we're going to do 1 as our second point. So plug in 1 for x, and then follow your order of operations to get -15 as your y. And so our second point is going to be at 1, -15. And then take all the information and graph it. So we have our axis of symmetry at -1. Our vertex, we plotted our 2 points on the right, reflect them to the left, and then draw your curve. All right, in this last section, let's talk about interpreting quadratics in real-world applications. So what we want to do is figure out what wording in a word problem refers to what key feature, okay? So let's talk about maximum height. If we were to talk about what our maximum height is for something that's flying through the air, the path that it's taking through the air is going to be a parabola. It's going to go up, it's going to go to a maximum point, and then it's going to come down. And it's going to be that curved parabola shape. So if we're talking about the maximum height, the height is going up and down. And what axis goes up and down? That's our y-axis. So our maximum height is going to be the y of our vertex. How long does it take to reach maximum height? Well, if we're going out in time, we're going horizontally out. Okay, so it's going to be the x value of your vertex. The starting height, that is going to be your y-intercept. Okay, because we don't know what the height is, but we know at the start we're at time 0. Okay, and then the time it took to reach the ground, that's going to be your x-intercept. So let's see what we can do with some examples. Selecting appropriate key features provides the procedure for determining the solution. So the height and feet of a football that is kicked can be modeled by the function that's given here, where x is the time in seconds after it's kicked. So we want to know what was the starting height of the football. Well, if we want to know the starting height, then we know starting time is 0, so we're going to put in 0 for x. And when we do that, we find that our starting height was at 0 feet. How long did it take for the football to reach its maximum height? We're talking about the time, so we're talking about the x value of our vertex, and the x value of our vertex is our axis of symmetry. So we're going to use x equals the opposite of b over 2a, which is our standard form axis of symmetry, because this equation that's in the problem is in standard form. B is 64, a is -16, and so we are going to evaluate that and get 2 seconds is our answer. So what was the maximum height of the football? Well, we know that it reached its maximum height at 2 seconds. That's our x. So we're going to plug in 2 for x and evaluate our function at 2. And that's going to give us, when we do the math, 64 feet. In example 6, as Molly dives into her pool, her height in feet above the water can be modeled by the function given here, where x is the time in seconds after she begins diving. How high is the diving board? Well, she is starting at the diving board, so that's going to be at time 0. We plug in 0 for our x, and we get our y-intercept, which is 12 feet. How long did it take Molly to reach the maximum height of her dive? Well, we use our axis of symmetry because we're looking for the x of our vertex. So the opposite of b over 2a, we plug in b, we plug in a, and we evaluate and get 0.5 seconds. And then we can plug that in to find what the maximum height was. So you plug that in. Here I suggest that you just plug this into your calculator. And when you do, you get 16 feet. All right, so that finishes off this section on doing some graphing and doing some interpretation of quadratics. Coming up in the last section, we're going to talk about quadratic transformations.